What's up, Patty? We hear you, baby. Hello, come on in. We're about 3 minutes early. You're welcome to ask any questions you might have. The lighting in this room is not doing so good. When I get close to the computer, my whole face and everything turns red against this purple. It's not looking, looks like I'm about to have a stroke or a heart attack or something, but I'm not. I'm fine, I think. It's a free time to ask any questions you might have, folks. We're going into chapter 25 now. Oh, sorry, I got itch. But you can ask me anything you want. Test 2 should come up, as well as some more practice tests should come up sometime within today, tomorrow, or this weekend. So just be prepared for that. Hopefully everybody got their test done. That was due last night. Hopefully. I have a substitute teacher for today. There's no way to get into focus without like putting it so far back where you can see it. I was going to move it up, but yeah, that's cool. I usually have that on my hat, and I've lost it like 6 months ago. I just found it laying on the floor of my office. So I'm very excited. It's a wonderful, wonderful day for me.
That's cute.
A slothstronaut. All this time, I thought my daughter's been a fan of sloths, and I make these funny jokes about the movies Zootopia with that sloth looking in the DMV. And come find out she does not like them. They creep her out. So I do that slow expression where he's about to break into a laugh after he tells a joke, and it just freaks my daughter out. But it's kind of fun. You guys are just not keeping the conversation up here. I'm gonna have to start talking about Napoleon or something. Napoleon. Your book mentioned Napoleon. That's why I happen to be thinking of it. There goes my cat. Hey, Allie. Oh, she's running around. You busy, girl? You busy to come see me? Okay. What's up, Allie? All right, it's officially time for class to start. So ask yet again. Anybody have any questions? The test was last night. Hopefully y'all did well on that. Of course, you had multiple attempts and all that good stuff. I plan to keep it that way. I should be able to. I was telling everybody a few minutes ago. I should be able to have at least test 2 and probably 1 or 2 more practice tests posted sometime between tonight's class and this weekend. So you guys can get started on that. I also got to keep a track of the chapter questions because I make those little chapter quizzes. Students have actually said they wanted that this semester for the first time. I'm from what I've heard so far from the few students that have responded this semester, they like having them. So if you feel otherwise, let me know, because it's takes a little bit of time to do. So it's kind of a pain in the butt. But anyways, I don't mind doing it if students are using it and you guys kick butt and make like hundreds on your midterm. That'd be awesome. So no questiones. No questions. Quid, Quimodo, Quis. All right, well, let's get started then. So this is chapter 25, and chapter 25 is actually called electric current and resistance. So as you might suspect, we're probably going to learn a little bit about electric current and a little bit about resistance. In fact, this particular chapter 25 does discuss current. It tells you about batteries, which I've already alluded to how to make a battery and why they're called piles and that sort of thing. It tells you about the terminals, and of course you've already learned about electroscopes earlier. It mentions electroscopes, and basically Galvani had discovered that when working with dead frogs, for some reason they were randomly kicking, even though they were supposedly dead, which I'm sure was a startling thing the first time you see it. Later he determined that it could actually happen by anytime he stuck two different metals in one of the leg muscles of the frog. Of course, he ended up finding out that would work for frogs, and actually made a really big kick. He thought, for instance, that was maybe the soul or something like that, animal magnetism or weird stuff like that. But that was some of the concepts. However, Alejandro Volta suspected otherwise after the publication and thought it might be a result of the dissimilar metals. So now pretty much all you have to do, and you can use, your book makes a point to let you know, you can use one of the metals as carbon, even though carbon I don't think of as a metal, and I don't think I know anybody that thinks of carbon as a metal or even a conductor. But the main thing is two dissimilar metals, and if you take one by one the various pairs of metals that you can run across, you can actually build what's called an electronegativity chart. And basically the one that wins the electrons will be up at the top, say, and then the ones that loses the most electrons will be at the bottom. And from that thing alone, you can tell whether, if you rub rabbit fur against let's say plexiglass, you can tell immediately, if you've done those particular things, rabbit fur and plexiglass, you can tell immediately which one's the one that actually donated electrons, which one's the one that actually accepted electrons, that sort of thing. But anyways, Volta believed that, and he ultimately made what we call a pile, and there was a very good reason for it called a pile, because basically you could just take two metals. He took silver and I can't remember, I think it was zinc and silver. Yeah, zinc and silver was the ones he took. You can do any of them. In fact, when I teach this at like hands-on science museum in Elizabeth City called Port Discover, when I do that with kids over there, we'll take it's amazing how much you can take. You can use a potato, a tomato, a lemon, a lime, an orange, just about anything. I've even done it with a banana. But you can take like some number 8 or number 10, or maybe even a little smaller than number 8 if you wanted to, maybe even smaller than number 10, say 12 or something. And you can take that without the housing on it, make sure some of that stuff that has laminate, and you can just jab that in one side of those fruits or vegetables or nightshades, whatever you want to call it. And then you can take a galvanized nail, which is basically covered in zinc and some other stuff. You can stick that in the other end, and lo and behold, you can take a voltmeter and touch the two metals, and you will in fact get a voltage across it. Now, if you take whatever fruit you use, say it was a lemon, and if you connect the nail of one lemon to the copper wire of the other lemon, then you can go across both of them and you'll get twice as much voltage, and you can keep doing that over and over and over again. So that's actually ultimately what was done, and you can build a pretty significant voltage that way. Initially, they called that little thing a pile, or one little part a cell, and then you just take and build a cell, and then you could add as many cells as you want in series, and that would make as big a voltage as you want as well. In fact, that's not a lot different today. For instance, you can open up one of those 6-volt batteries that you'll sometimes see at Home Depot or Ace. It's like rectangular and it's like 6 volts or something like that. And I don't recommend you opening it up. These are things that I did before I had any knowledge of dangers and stuff like that. I just did them because I was curious and I ripped stuff apart. But there's acid in there, some carcinogen things, all sorts of stuff. But if you open such a battery up, you'll find there's like a bunch of little D batteries in it. Even though they're not, it's not like a labeled Rayovac or Energizer or anything like that. It just, you can tell they look just like D batteries or just like C batteries, or in some cases just like AA batteries. And they just stack them all together in such a way that they're wired in series until they make 6 volts. And if they actually want them to just be 6 volts, since the nominal voltage of a D battery is like 1.5, you can just put 4 in series. But if you want it to last a long time, then you can put 4 in series and parallel with 4 and parallel with 4 and parallel with 4 and parallel, and then your battery will last even longer. So that's ultimately how it happens. This elliptical trainer behind me, cross trainer, the battery died on that, and I took the old battery, opened it up, and sure enough, there's just a bunch of smaller batteries in it. So it's kind of interesting how at the end of the day, no one's really making anything other than like AAA, AA's. Well, obviously those watch batteries are a little different, but AA's, AA's, C batteries, D batteries are pretty much the way everything works. Car batteries are different, of course, too. But the main thing is, if you have what we call an electrolytic solution, which could be Gatorade, as you know, Gatorade provides electrolytes. So that is actually true enough to work. I've done it with apple juice. I've done it with vinegar. I've done it with just whatever juice is inside, and that includes just the moistness of a banana. Okay, but it can generate that voltage. Now, what is that voltage? Well, we learned earlier when we covered voltage that was the potential energy per unit charge. In fact, 1 volt is defined to be 1 coulomb, or excuse me, 1 joule per coulomb. So it's literally a measure of potential, but we don't say potential energy when we say voltage. We just say electric potential, and then everybody knows we're talking about volts. Whereas if you say electric potential energy, then we're talking about joules. But that, because of that parallel with energy, it pays dividends to think of a battery, say, as a almost like a pump or an escalator. And escalators are probably a good idea, because the way I want you to think about a circuit is, let's imagine, actually I have a wire here, this will work. Okay, so let's imagine you have a series of wires and a power supply, which would be like a battery or something like that. If you actually had one of those, what you need to think of the battery as is something that lifts from one height to another. So I've got this hard drive here. So you can imagine that the wire comes from something else, maybe from a resistor or whatever, and just comes in at the bottom of this power supply. And this power supply lifts the energy up here. And what it really does is it compels positive charges to run away from this part, or you can think of it backwards, which is the reality, by the way, that positive charges running around is what we call conventional current. And there's really only one major experiment you can do to tell which one it is. So you can pretty much always pretend conventional current's okay. But the real scenario is actually that this side compels negative charges to run through the wire, and then the wire will go back up, run into something that in this case would actually lift it to technically a lower voltage, but a lower potential energy for the electron as well. And then it'll be a flat wire that comes back around to this. So you think of a circuit such as a battery in parallel with a resistor, actually technically in series with a resistor, then all you should think about is basically, hey, I'm going to go from this wire, which has negligible resistance. So if I go from the end of the last resistor horizontally to the battery, then the battery is going to lift everything up. And then I run a wire again horizontally, come back towards the screen and go back this way. And then I run to the top of the resistor. What's going to happen is the resistor then acts like another escalator, this time taking the charges down. Now we're back at the original height of the wire. So I go down, around, and come back in. The reason why you'll see that type of explanation of circuits is because it is a good analogy. It's a good analogy specifically because the equations work the same way. So the only difference being, of course, potential energy would be mgh, whereas electric potential would be potential energy divided by the charge that's going to feel that potential energy. So a high voltage means positive charges would run away from it to a low voltage, whereas electron will actually run away from low voltage to run to a high voltage, specifically because the potential energy and the voltage differ by this by dividing the potential energy by Q. And when Q, the charge, is negative, then obviously you get a voltage and a potential energy that have opposite signs. Okay. So it leads us to discuss the problem of, well, what exactly is the current part? Because I've told you about the voltage part being sort of potential energy per unit charge. Well, the current part you can sort of imagine is that pump lifted up, say, water molecules from a garden hose as opposed to a wire. But in reality, what it's doing is, and it doesn't have to supply, it doesn't have to, the charges don't have to physically leave the wire, but essentially what's going on is negative charges are coming into the negative side of the battery. The battery is then lifting them negative charges up, but in reality, a net number of negative charges are moving through the wire, but they don't actually have to leave the wire. They're doing their work just by changing the energy, and then no actual charges necessarily have to leave the battery either. But again, they're doing something equivalent to that. And then the negative charges, of course, would then come out of, say, or excuse me, it would come in to the negative and then it come out of the positive and run around. So if you think of the charges going through the wire as sort of like molecules of water going through a water hose, if you kept count of the amount of charge that passed one spot, say, in the wire, and a unit of time of 1 second, then you'd have what we call amperage or current. So current is the flow of charge. So let me start by sharing my screen here. Anybody have any questions so far on this? Hopefully this is somewhat familiar to you, just a little bit from everyday life, a little bit from, high school science or middle school science or something like that. If it's not at all familiar, that's okay. You just might have to do a little bit more reading and maybe even do a little bit more Google searches specifically for interesting things that help you understand how circuits work. I highly recommend Veritasium, by the way. I'll write that down here. So Veritasium. Physics girl used to be pretty good. I assume she still is. I haven't seen her in a while. She got away from one sponsor, and since then I haven't seen her very much. I think she might be with, I don't know if she's with PBS now or what, but that's another one. You can look at Crash Course Physics, and of course Crash Course Physics is with Dr. Shinny Samar. Actually, it's Samara. But all of these are good resources. What am I writing here? Crash Course Physics. I don't know. Yeah, so Veritasium. Oh, Physics Girl. Okay, so all of these are resources that you can use that are actually reputable. Most of what I've seen with Wikipedia with regards to physics and mathematics, I've actually found to be mostly correct, other than a typo here and there. So yeah, the cardinal rule in academia is, yeah, you better not be using Wikipedia, but you can certainly use Wikipedia to sort of get a feel. If you're talking about, again, math and physics and chemistry, I get plenty of accurate information straight from Wikipedia in that sense. But you can read it, get an idea of how to understand whatever topic you're talking about, and then look at what they're actually using as sources, and then you use those as sources. That's what you want to do in an academic setting where you're writing a paper or whatever. But definitely look up Veritasium. As we said, we found that the voltage, and I'll say change in voltage, is actually the change in potential energy divided by the charge Q. Okay, so we already knew that that was the definition of voltage, and that's how we know that the units of the volt is equal to 1 volt, which is defined to be 1 joule per coulomb. And now I've suggested that if you look at a wire, let's say we have a nice little wire right here, and we're just looking at a small part of the wire, of course. Okay. But if we look at just this part, say, okay, and we're looking right along this line, and we see a charge delta Q go by in a time delta T, then this would be your average current. And from that, I think you can see that the units for current are, let's say, 1 coulomb per second, which is defined to be 1 ampere. That's a capital A. It's called an amp or an ampere, named after obviously someone with the last name Ampere. Okay, we'll learn Ampere's law later, so you'll get a little bit more familiarity with them through that. So this is what we call current. And this is what we call voltage. But we also call it electric potential. Whereas this we call potential energy. Okay. Now, in general, since that's the average, you might reach the conclusion, rightly, by the way, that current is the instantaneous rate of change, if you will, of charge. And that's exactly right. We'll say I actually is dq dt. And sometimes you got to be careful if you're talking about the current, say, leaving a capacitor. And sometimes in such an instant, it is the fact that it's causing the charge on the capacitor to go down. If you're talking relative to the capacitance, what's the charge doing? Then you'd say I is equal to negative dq dt, because the charge of the capacitor is leaving the capacitor to create the current. So you'll sometimes see that we'll slip in a I equals negative dq dt. Always pay attention to that. And that's, that's partly what the sentences and the paragraphs that are in your textbooks are about, is making sense of the stuff. So in an ideal world, everybody is skilled, intelligent, bright enough to just look at examples in a textbook and then use that to solve physics problems. In reality, sometimes you need more than just the example. The examples can get you a long way, but you're not necessarily understanding the big picture. You're more likely just sort of regurgitating certain actions when you see certain problems. So if you see a new problem that's not like one you've seen before, you don't have any idea where to start. That's what we're trying to avoid. Is we want you guys to, and I apologize for using the phrase guys, but just, old-timey people talking like that. So anyways, what we want you to do is be able to think of ways to solve problems by thinking of what variables the problem depends on, and then think of how to apply equations relating those variables, stuff like that. So now we've gotten an issue relating voltage and current. We have some idea of it. In fact, you've already had a lab. Actually, you should have had, have y'all had your lab yet this week?
Yeah.
Yes. So y'all did series and parallel circuits, yes?
Yeah.
Okay, cool. So you've now had two labs then. Thanks for answering me, by the way. You've now had two labs, one of which covered Ohm's law. And that says that V, the voltage across any object, is equal to I, the current going through that object. Notice the word that I'm using. I use voltage across things, and I use current going through things, That voltage is equal to the current going through the item times what we figure to be the resistance, or a measure of the resistance, at least at that point in time, of the object. And that's Ohm's law. Now, what that means is if we're dealing with ohmic devices and we make a graph, let's say we put current on the horizontal axis, let's say we put voltage on the vertical axis, and then you get a nice little line like this, then you know that slope is equal to a constant because it's a straight line. And in fact, it's equal to R, the resistance. Okay. But as we saw in our Ohm's law lab, there's also times where the voltage versus current graph looks like that, in which case you can tell the slope here is about that, whereas the slope here is about that, and the slope here is about like that. That's a non-ohmic device. So I would differentiate them by calling this non-ohmic. And I would call this one ohmic. Okay, and I got another person came in. So that's some of the stuff we learned. But remember, the equation V equals IR is always relevant in that if someone wants you to give some reckoning of what the resistance an object is at some point in time, if you have a way of measuring the voltage across it as well as the current going through it, then you can just divide the voltage by the current, and that'll give you the resistance in ohms, at least for that split second, which like I showed you on the near parabolic graph is just a slope at a particular T or I or whatever. So any questions on that stuff? Okay. One thing you should know is also, I'm sort of trying to give you guys some of the fundamentals that are going to come up a little more handy in the next chapter, especially, but from your lab, some of the stuff you should have learned by now is, I'll write these as, no, I don't want that color, lessons from lab. Okay. One thing is electric fields are perpendicular to, anybody recall the name of one of the things that an electric field is perpendicular to?
Equipotential line.
Exactly. Very good. Equipotential line / surface. Okay. So that's one of the things we learned. And because of that, we were even able to draw the actual electric field lines for some neat configurations. Two, we should learn that multimeters measure voltage. Oh, that's off an E, called electric potential. and current and other stuff. When measuring V, they are acting as voltmeters. Similarly, measuring I implies they are ammeters. Okay. Voltmeters that's just ugly. I don't normally write this much on a slide, but I kind of want to here. So voltmeters measure the voltage, actually, across the object they are in parallel with. Okay. Now, the reason I write that sentence is I want you to remember, if I ever want to measure a voltage, the first thing I have to do is make sure I put the voltage setting on the multimeter to voltage, and I would recommend to the highest setting for voltage so that you don't accidentally overburden the meter and blow a fuse. But the second thing you do is then you put it in parallel with the object whose voltage across which you care about. So if you're trying to measure the voltage across a resistor, then you take the side of the resistor that's closest to the red side of the power supply or the positive side of the power supply, and you connect that with the red cord. Again, the red and black cords have no meaning whatsoever other than they're just convenient. They don't act any differently. But when I say red cord, I mean the cord that's plugged into normally the red outlet that says V omega on the multimeter. And then you take the black COM port and connect that to the other side of the resistor. And by doing so, you can see that if an electron or a positive particle came to where the multimeter was attached to the wire, at that point, that charged particle has a choice to either go through the meter or go through the resistor. That choice is what makes that a parallel setup. Does everybody get that? So that's the whole purpose of what I'm saying in this all of number 2 is I'm reminding you that voltmeters should be put in parallel. And the next part is ammeters should be in series with the object carrying the current. you want. Okay, that's another big deal. Actually, the biggest problem is people will set up a voltmeter correctly, but they'll have it set to ammeter setting, and then what happens is if you don't have a good enough fuse, then you've basically ruined the meter. I got to write a lot bigger than that. There you go, that makes it look a little better anyways. So ammeters should be in series. Oops. So those are two big rules you're supposed to learn from the lab. There's a couple more though. Number 3. Oops. Yeah, we're doing that in green. Number 3. The total voltage is equal to the sum of the voltages that are in series with a battery or power supply. So what I mean by that is let's say this is 15 volts. Wire goes out, wire goes up to here, runs into this voltage, runs into, excuse me, this resistor, runs into this resistor, and then comes back. This resistor is called R1, R2, R3, and the voltage is V1, V2, and V3. So 15 volts is equal to V1 plus V2 plus V3. Now this also has a current I total going through it. And that brings us to our other rule. The current through each of the resistors in series is equal to the current supplied by the battery. So this means I total is equal to I1 is equal to I2 is equal to I3. So hopefully you learned that a little bit yesterday and or whenever you did your lab. You learned that in the series and parallel lab. 4, if any number of resistors are all in parallel with each other, then they will all have the same voltage across them. So what I mean by that, let's draw a circuit again. This time I'm going to go up, I'm going to run into a resistor. Run into another resistor. And run into another resistor. Okay. So this will be R3, R2, R1, I total, I1, I2, and I3. And what we're seeing is V1 equals V2 equals V3 equals V for the battery. Similarly, I total is equal to I1 plus I2 plus I3. Okay, and that's just conservation of charge. Notice as that current I total gets to the junction between the vertical wire and the horizontal wire going to R1, it has a choice there. Whenever you run into a choice, you know something's in parallel. In this case, it has a choice of going either to the right through R1 or straight ahead, which could result in going through R2 or R3. So that clearly means R1, R2, and R3 are all in parallel. And if you had, say, I total being, let's say, 150 amps, and you found that 50 of them went through R2 and 75 went through R3, then you know R1 would have 25 go through it. Okay, that's what we're saying. So these are some ideas about circuits you should know from your lab by now. I didn't write the part about the currents. I didn't write that in green. I just did it in symbol form. Hopefully that's good enough for you guys. But I wanted to make sure y'all had that somewhere. What does that mean in terms of connecting a circuit? Let me just show you how you connect a circuit. So for instance, if I had, let's say, a battery right here, okay, and then I come up here and I go to a resistor, R, if I wish to measure with a voltmeter the actual voltage, I would say, if I remember correctly, I think it's on the right hand side, V omega. I would connect this to right here. And then I would take this, I'd jump over that wire, and I'd connect it right there. I would have to make sure this is set to V. Okay. Similarly, if I had a circuit, if I had a circuit like this, and I ran into a resistor R, okay, what I would have to do now is I'd take my same multimeter and this one would be amp, say. There's the COM. What I would have to do then is take the wire from the red one. I don't know why I just drew that black. I thought I hit red already. Take the wire from the red one and connect it there, and then take the wire from the black one and connect it there. See how I had to break the circuit, and every particle that goes through R has to go through the ammeter? That's the key. Okay. And this one must break the circuit to put the ammeter in. Whoa. Okay, any questions on that, folks? All right, so I know that that stuff's not all that exciting, but it's stuff that we want to know, we want to have in our mind. I want to make sure everybody sort of has gotten to the point from doing their experiments that they now sort of own that information via experience. Okay. If you haven't, then you need to look back over your lab, read back over the procedures, think about what you did, and make some sense of it. Okay, because that's what you're supposed to have picked up from labs so far as a bare minimum. Let's just put it that way. Okay, if you don't have that stuff, then maybe you weren't attentive enough in class, or maybe you worked with a group that went too fast and you were left behind. The main thing is, if your teacher or me, if you were my student, for instance, happens to give you a final exam for the lab, you're not in a good spot if you don't know these things. All right, so any questions on that? So we can go ahead and jump right in and start looking at things like simple questions, like for instance, how much current goes through a particular circuit. You can ask stuff like that, or you can say, all right, if I know the voltage applied to a flashlight and I know the amperage going through it, what's the resistance at least at that instant? So let's do an example. Okay. Let's say an electric razor uses a single AA battery and draws 300 milliamps through it while it is running. Oh, dang it. Keeps erasing. What is its apparent okay, I'll tell you what. Dang, I'm mad. What is its resistance? Oh, that was bad. Okay. So this is an actual motor. So you don't necessarily think it's necessarily like an actual resistor, but still in some sense it has some resistance, and that's what we're using. What we know is solution V equals IR. Now, what I normally do, as you've seen, is I normally would take that equation and solve for the thing I want to know, for instance, R, and I'd write R equals V over I, and then I'd plug in the V and then plug in the I. But I'm going to do this more like most of my students tend to do it. I'm going to write the numbers in place. Now, for starters, what you should know, and you might not, and that's perfectly fine, but when companies or manufacturers ask for AA or AAA batteries or C batteries or D batteries, then they're expecting a nominal voltage of 1.5 volts. Okay, so that's the first thing we got to realize. V equals 1.5 volts. Now, to be honest with you, when you first buy that battery, even if you connected it up to a load and then you put the voltmeter in parallel with the battery, the voltmeter will tell you that the battery is probably 1.72 volts or 1.68 volts or something like that. But that's just giving it enough buffer so that you can have it for on the order of a year before it ever reaches 1.5 volts. I say on the order of a year. I'm just making figures up, but obviously battery manufacturers do not want your batteries dying, but for so early, right? So that's just something you should know. AA, AAA, a lot of others too, but definitely C and D batteries as well are that. The little rectangular batteries that you see where they've got, two little round ends on each, both of them on the same side of the top of the smaller rectangle. That's a 9-volt battery. So you'd expect it to be 9 volts. It's probably going to read like 9.8 or something. The big square ones that are like 6 inches tall by like 4 inches by 4 inches that you see, they're usually 6 volts, stuff like that. Car batteries, 12 volts generally. Motorcycles can have 6 or 12, so be careful with that. In fact, I fried my electric system on my Suzuki a little bit by trying to jump it with a car. I was pretty confident it was a 12-volt battery, but it was not. Okay. All right, so here I am. I'm going to put in the voltage. 1.5 volts is equal to 300.0 milliamps. Now, I suspect and I hope most of you are saying, I object, Mr. Younger, you got to convert that to amps. And really, you can. And in many cases, I've been teaching you the whole last semester that you should. But to be honest with you, when you get in electricity and magnetism, a lot of times it's just as easy to leave them in there. So what I'm going to find here, for instance, is R, and R is going to be 1.5 volts over 300.0 milliamp. A milli in the bottom is the same thing as a kilo on top. That's why I don't necessarily get rid of it. Now, what I am going to do is something neat. I'm going to call that 15 volts by multiplying by 10. And then I'm going to call this 3000 milliamps, okay, by multiplying by 10 on top and bottom. The reason why I do that is I know that this front 30 right here is twice as big as 15. So in fact, I'm going to get 1.5, or excuse me, 0.5 for the 15 over 30. And then I'm left with, basically, I've used the 30, so I'm left with a, I think that's a 1, 2, 3. So I'm left with 2 zeros. So that's divided by 100. And that's kilo ohms. So I'm just avoiding using a calculator, in other words. So this is 0.005000 ohms, or excuse me, kilo ohms, which I can also write as 5.0 ohms. Okay, so that's the only reason why I left the milliamps in there that time. A micro in the bottom becomes a mega on top. You can even work with things like a micro divided by a nano and see what that comes up with, all sorts of good stuff. Now, what if, so part B, what if the battery weakens to, let's say 1.2 volts? What then will be the current? Okay, now I haven't introduced energy, but that begs the question right here is, what's the power in both cases? And one formula for power is current times voltage. So what you'd see is that's the problem. You don't know necessarily how many amps your shaver needs. You don't know how many volts it needs necessarily, but you can readily find out on electronic equipment and stuff that you buy what the power requirements are. And those power requirements are what's super helpful to a consumer to basically prevent themselves from having a fire. So for instance, if you could connect something to an extension cord that has a large power output, then you have to assume that's going to be the power input, and the voltage, if it's AC, you're going to call that 120 volts, and you take the power and divide it by 120 volts, and you'll get a certain number of amps. If your extension cord isn't big enough to hold that extension cord will eventually get hot enough, melt, it could burn you, it could set your house on fire, all sorts of stuff like that. So that's the disadvantage right now, is I would really like to take the time and calculate the power in both cases, but I'll show you power in a second, so it's not that big of a deal. So let's go back to red and look for my solution. So in this case, we know V equals IR, but now we've got, and that's a question mark, by the way. I noticed how little it looks like a question mark. Let me change it to blue. Much better now, absolutely. Okay, so I'm going to say 1.2 volts is equal to I times, let's say 5.0 ohms. In other words, we're assuming the motor is going to take just as much resistance. That may or may not be a good assumption, but the main thing is that's what we're doing. Okay, so I is going to equal 1.2 volts over 5.0 ohms. I did not like how that wrote either. Okay. I know 120 divided by 5 would be 24. So this should be 0.24. amps, which is 240 milliamps. Again, I'm just trying to avoid using the calculator. Okay. So that's why I did the times 100 and then divided by 5, just to try to make the math something easy. Any questions on that problem? Okay. Also, hopefully you learned from lab that resistors have basically little color bands on them, and that there's a table you can use that tells you what each color means. The first two are in fact numbers that tell you what we call the mantissa. The mantissa is the portion of scientific notation number that precedes the times 10 to some power. So the mantissa is given at least 2 of the digits by the first 2 colors. And then the multiplier is the third ring or the third painted stripe. And that could be like 10 to the 1, it could be 1, it could be 10 to the 6, all sorts of stuff. And then there's often another line, which would be a fourth one, and that tells you how precisely you can guarantee that. So for instance, if you read a resistor and it's supposed to be 3,500 ohms and the tolerance is 2%, what that means is you can expect it to be within plus or minus 70 ohms, because 2% of 3,500 is 70. So it could be as high as 3,570 or as low as 3,430. Does that make sense to everyone? All right, so that's just some quick calculations in my head. We also use, another thing you should keep in mind, we use conventional current, and that means we're pretending positive charges are leaving the positive/red side of power supplies and then re-entering the negative/black side of power supplies. There is an experiment called the Hall effect, like a hallway, HALL, not named for that, but basically what happens is if you subject it to a magnetic field and run current through it, basically you'll get a difference in voltage from one side of the wire to the other. And if it's one way, that means it's positive charge carriers. If it's another way, it's negative charge carriers. And when that was done, we finally figured out that Ben Franklin, who chose somewhat arbitrarily which ones we called positive, which ones we called negatives, he had a 50-50 chance and chose incorrectly, but still we have positive and negative charges thanks to Ben Franklin. So any questions on any of that kind of stuff? All right, some other things we need to understand is I drew a wire earlier a few minutes ago, and I want you to have some idea. Well, I want to see what ideas you do have. So let's imagine first, I'm going to take a wire. Okay. Okay, now I'm going to take a wire. This is the area A1, and this is the area A2. So which one is harder to go through? So you can imagine this like it's an actual pipe, and you can imagine yourself being any size you want to be. But what you want to do is see which one's going to be harder. So you need to make yourself a certain bigness. So under those conditions, which one of these wires is harder to go through? The top one or the bottom one?
The top one.
The top one. Okay. Okay, so the difficulty you have in pushing a certain amount of current through a wire is called its resistance. We've already ran into that. So what this means is R1 is greater than R2, and you might even reach the conclusion that R is inversely related to A, because A2 was bigger than A1, and because it got bigger, it made the resistance less. So do y'all agree with my assessment? I'm not saying that it's not A to the 2 power, A to the 3 power, A to the 4 power. That could still be the case, but we definitely know that when A goes up, the resistance goes down. Would y'all agree with that assessment? Anyone? I should have at least put the chat up here so maybe I could see. No one's chatting the answer either. Okay, so yeah, definitely, because the ease with which it would be to, let's say we're rescuing elderly people from a home that's being engulfed by flames or gas or something like that. You have one hole in the wall that's only 4 foot diameter and another hole in the wall that's 16 foot in diameter. Obviously, if those are your only two choices of how to get the elderly people out, you're going to send them through the bigger one. Okay. So that means the resistance that you run into would be worse for the smaller one. So the resistance must be inversely proportional to A. It does turn out to be exactly to the first power, by the way. Now let's look at another 2 wires. In this case, I'm going to say, here's one wire. Well, that was helpful. Thank you for that. Okay. So this one has a length L1. This one has a length L2 less than L1. This was A2 greater than A1. So which one of these is harder to get through? Okay, so you've got your Dr. Nefario cart. If you've seen Despicable Me, you know that was Dr. Nefario was the evil scientist that worked for Gru, and he rode one of those little jazzies like you see people riding in the grocery store if they have certain problems or whatever. So which one of these is Dr. Nefario going to get through faster, the short one or the long one?
The short one.
the short one. Therefore, the long one's the harder one, right? So because of that, see. Causes more difficulty. Which implies R is directly related to the length. Okay. Again, I'm not necessarily saying it's the first power, the second power, the 1/2 power, the third power, or something like that. I just know it's thumbs up, thumbs down. So the longer the wire, the larger the resistance. So we've reached two pretty big conclusions. And in fact, it turns out experimentally, all you need to do to make an equation instead of a proportionality, that's what those little fish looking diagrams are. They're just showing proportionality. It turns out to make an actual equation, all you have to do is write rho is equal to, or excuse me, R is equal to rho L over A, where rho is called the resistivity. In other words, we've taken into account the cross-sectional area of the wire. We've also taken into account the length of the wire, but what we haven't taken into account is what's the wire made of. Clearly, a carbon wire is going to be a lot harder to get through than a gold wire. So in fact, this resistivity is what allows us to do that. And in fact, your table or your book has a table of resistivities in it, and you can use those to solve problems, for instance, stuff of that sort. So for instance, in chapter 25, I'm trying to think, actually, let me look, see if I can see from here. Oh yeah, it doesn't really give page numbers necessarily in the electronic book, but either way, there is a table of resistivities. And to give you some idea, the resistivity of silver, which we know is Ag, is equal to 1.59 times 10 to the negative 8th. And notice the unit, it's an ohm times a meter. And it looks like that 8 got a little ugly, so I'm going to make that a little better for you guys. And not only that, it looks like that negative might be misconstrued by where it is. Okay, so that's the resistivity of silver. The resistivity of gold, which I think you recall is AU, that turns out to be 2.21 times 10 to the negative 8. Again, ohm meters. What about the resistivity of copper? Okay, that's what a lot of wires you normally run into are made of. It turns out that resistivity is 1.68 times 10 to the negative 8 again, ohm meters. And in fact, my dad retired from Dominion Power, and he told me a lot of wiring is done nowadays with aluminum because it's so much cheaper and lighter than copper. And it's really not horribly bad. It's way cheaper than gold, of course. So it turns out the resistivity of aluminum is actually 2.65 times 10 to the negative 8 ohm meters. Okay, now that's one equation that's very important. It tells us how to calculate the resistance of a given object. If you know the cross-sectional area, you know the resistivity of the material it's made of, and you know the length that it's got to go through, then that allows you to calculate the resistance of that object, even if it's not a resistor, even if it's like a piece of aluminum rod or something like that. It turns out, though, as you might suspect, just like if you're, let's say you're at an old folks home and they're just sitting down watching sorry, old folks home might be a sort of rude way of saying it. Let's say you're in a retirement home or a retirement community and there's people calmly sitting still waiting for the bingo guy to call out the bingo numbers, and you want to walk from the front to the back, actually from the front right to the back left, that would take a little bit of time. But if you replaced all those bingo players with a bunch of people from 17 to 27 years old dancing, I suspect you'd figure out that the dancing crowd would take more time to get through. So similarly, if you actually increase the temperature of the metal, then you're going to actually increase the resistivity of the metal. And there's a distinct equation that we can use for that. It looks a little weird, but you could think of it like this. You could say that the change in resistivity is equal to, let's say, the original resistivity, let's say alpha, times the change in temperature. That seems kind of reasonable, right? If the temperature goes up by a certain amount, then rho final minus rho initial is going to go up by a certain amount, just like T final, T minus T initial did. So if you actually look at this, you could say, well, this means rho minus rho zero, where I'm now going to call the temperature, the initial temperature T sub zero instead of T sub I. I'll say that's actually equal to alpha times T minus T sub zero, right? Then you'd get rho is equal to rho zero plus alpha times T minus T zero, and things start to look a little bit odd. Well, it turns out the equation that we ultimately use is in fact rho at a given temperature T is equal to rho zero times 1 plus alpha parenthesis T minus T zero. And I think you can see that's identical to what we had before. To some extent, because actually I should have written this as times rho zero. That's what I left off. So if I had written that way, then it would have been right. But that's where that came from. I just forgot to put that on there. It should make some sense that if your resistance is really, really high to begin with, then it might not take very much to get it to go a lot higher. But if your resistance is really low to begin with, it might take a bit more. So that's a way you could justify the rho zero being in there. If you felt some compunction to make that to be the case. I'm not sure you will, but anyways, there you go. All right, so that's the actual equation. And it turns out it also works for straight resistance. So I can also write R is equal to R0, and I'll call this R sub T for temperature at T. And that's equal to 1 plus alpha T minus T0. So those are the equations you use. Now, ideally, you can find tables, for instance, in your textbook, that same table that had the resistivity, or excuse me, had the resistivity, also had the temperature coefficient. And that's what the alpha is called. Let's do it this way. I'll draw a red. Actually, I should have did something other than red since it was like that. I'm going to do a fancy color. I'm going to do green. That's called the temperature coefficient of resistivity. To give you some idea, alpha sub silver is 0.0061. Alpha sub gold is 0.0034. Alpha sub aluminum, let's say copper. Alpha sub copper is 0.0068. And finally, alpha sub aluminum is 0.00429. And all of the units, by the way, are Celsius degrees to the -1 power. Okay, that's what the actual units are. And I think you can tell why that's the case. These problems that involve using alpha or rho are really rudimentary. I mean, I could ask you something simple like, okay, I have to run a wire a distance of 100 miles. What size wire should I use if I assume I'm going to use copper? No, assume I'm going to use aluminum, and I want it to be no more than 1,000 ohms. Then all you're doing is basically solving for A, and then you could give me a radius. So these equations are really simple. I just wanted to sort of explain to you conceptually why they are what they are, and from there you should be able to, with what we've talked about so far, you should be able to answer essentially all the concept questions between that and your reading. But you're not necessarily ready enough to do all the problems. If you'll notice, though, I did change the dates in MyLab and Mastering, and in general, those dates are the ones that you can adhere to. If you ever find an instance where MyLab and Mastering said you still had a couple more days to do your assignment, and the Canvas gave you a 0 or something, you let me know, and then I'll give you full credit for it, because I'm always going to defer to the MyLab and Mastering, specifically because otherwise I have to change 5 different things. It's a nightmare to change stuff in Canvas. It's not so hard in MyLab and Mastering, at least not regarding the date. So you guys are free to go. Time is up. Class is supposed to be over at 6:40. At 6:39. I'll wait for the last person to leave, but I hope you all have a wonderful weekend, and keep an eye out for practice tests and tests. I'm uploading my notes to my Google Drive. So did any have any questions? Matt, Famata, you have any questions? Matt did not. How about you, Famata? Are you still there, huh? Sorry, I called you Hannah. I shouldn't do that. I always do it, but sorry.
Yeah, I'm sorry.
Okay. Did you have a question for me?
I was trying to see if I could pull it up. It was from the test. Hold on.
Okay. I'll set up so you can share your screen too then. Multiple people can share. Since you're pulling up a test, I'm going to go ahead and pause the recording.